I will speak about our joint work with Frits Beukers, which is a project. We have several papers, and this project started a bit earlier than the program, which was 6 years ago, but I think we did some advances on the ideas which I'm going to present just here 6 years ago. And since then, it appears to be fruitful, and I will speak about an application to questions coming from mirror symmetry. So when X is an algebraic variety over a finite field, there are algebraic numbers alpha 1, alpha k, beta 1, beta m. There is k and m in such numbers, which are responsible for point counting over field extension. The numbers of points of X over the extensions fp to the s are given as sum of alpha I to the s minus the sum of beta j to the s for all s. So they are called Frobenius eigenvalues or Frobenius roots because there is an operation on p-adic cohomology of X or l-adic cohomology of X such that these are eigenvalues. The Frobenius operation it would be interesting to be able to compute such numbers and also to compute them in families. This is what my talk is about.
So do you mean p-adic cohomologies or l-adic, or you mean
both? I mean, there are different things which can lead to this.
But you're going to be using p-adic, so you'll be
I will do p-adic because it's explicit. And in the end, whatever tool you use, you get a matrix and compute eigenvalues. And we are going to compute such matrices, and this is useful for various purposes. The numbers are interesting themselves. For example, computing them for different primes and looking for distribution over primes is a big story, like Sato-Tate conjectures. But also there are different questions in which computation of these Frobenius eigenvalues appears to be useful. So when X is actually given over Q, we have something global and we reduce it mod P. This p-adic cohomology is just Dirac cohomology of X tensored over Q with QP, a completion of finite dimensional spaces. Which means that this Frobenius operation can be realized as an operation on differential forms. P-adic operation on differential forms. We will see it explicitly in this talk. Then I want to say that this is related to periods. And it is essentially p-adic. It doesn't fit in the Dirac cohomology itself. So to be honest, this is related to p-adic periods. But the result I'm going to present is related to actual periods because we are going to do families. So that was the motivation. We will look varieties over which are one-parametric families. This will be an algebraic variety over the field of rational functions. In this case, the Frobenius eigenvalues depend on T, and when n is the rank of certain homology group of X, which is a Qt vector space, or usually we do free modules over some localization of polynomials, but let's be simple and write that this is the dimension over of the field of rational functions. Then these are eigenvalues of some n by n matrices, Frobenius matrices. After you fix the basis in the rank of homology. So, what are these matrices? They are characterized by the following set of properties, and this is due to work, but also cuts. First of all, these matrices have something to do with periods in the normal, not p-adic sense. So, first, they are related to periods of the Gauss-Manin connection. On this module. Namely, the relation is like this. If U of T is the n by n fundamental matrix of solutions to this connection, then the Frobenius matrix, which is given by this expression, where lambda is here is a constant matrix. Of some p-adic constants. This first property says that Frobenius matrices satisfy a differential equation, and you can formulate it in terms of the Gauss-Manin connection. It's a differential system of order n squared. There are up to n squared parameters which give us possible Frobenius matrices.
But how do you look this fundamental as formal power series? Huh? I mean the entries.
This is my second property to formulate. The second property is that the entries are that phi of t has entries in the field EP, field of p-adic analytic elements. This is a very simple thing. It's the p-adic completion of the field of rational functions. So the entries can be approximated by usual rational functions modulo prime powers. And the third property is that phi of t with properties 1 and 2 is unique up to rescaling, changing of basis, simple rescaling by a constant. So you can just not quite. To compute, there is a unique solution to this differential equation, these properties 1 and 2, and then you can find the rescaling which will actually compute points. Phi means properties 1 and 2 is unique up to simple rescaling by a constant. And this is a theorem of work. Okay, so
sorry,
yes.
Very silly question, but the p-adic completion of qt, I imagine that should be qpt, right?
No.
You have
So what is the p-adic norm here? It's called Gauss norm.
that one.
You have one polynomial over another one, and the Gauss norm is the maximum of p-adic norms of coefficient upstairs divided by maximum of p-adic norms of coefficients downstairs. Or you can expand it in a Laurent series, and this will be just the maximum of p-adic norms of coefficients. Elements should be, like, if you reduce
Laurent or Padet?
Huh?
Laurent series or Padet?
Here it will be Laurent, but maybe I'm oversimplifying. So this phi of t, when you look modulo some p to the power s, it can be represented by rational functions. But when you increase s, denominators may grow. Okay. So the question we're going to solve is finding the lambda, which is unique, like identifying Frobenius structures. 1 and 2 shows them as a structure up to parameters, and then we need to compute the parameters. Yes?
So you are now starting from where x is defined over qt. How do you choose p? P is a prime number, right? How do you choose
Any
p?
prime, there will be a few bad primes, but yes.
So and the lambda, this my constant matrix lambda also depend. So
Okay, so this p, I'm choosing it at some point. So p is here. For different p's, we will have different matrices. They are unrelated, right? The story is different for each p. But we will see something which is, we'll see the construction in which p is a variable, and the results in actual computations, they will be given by formulas in which p is a variable.
But still, this is phi p of t.
Yes, this is phi p, and the story is for 1p. I'm not going to say anything about distribution over primes. I will just do one prime all the time. But the variety is given by an equation over z, and therefore we have this story of Dirac cohomology, and we can actually do it with usual differential forms, using some p-adic operations.
Also, when you say uniqueness, you mean after you've specified lambda, it's unique? Or there's only one lambda?
We have to make it a matrix, we have to do the choices of bases in
No,
Dirac
what
cohomology.
you've written is that there's only one matrix having properties 1 and 2, which is that there is some constant matrix. But you mean if you fix lambda, it's unique?
No.
Or do you mean
there
there's
is
only
a
one
unique
lambda?
matrix lambda
Oh,
up
also
to
unique.
multiplication by a number, just rescaling it by a number, for which phi has property 2. Okay? So property 1 basically tells you, look at matrices like this. Now, property 3 says there is a unique matrix lambda with some p-adic constant for which this has coefficients in the field of p-adic analytic elements.
You're fixing u or 0?
Yes, we fix u. We fix a basis in Dirac
Yeah,
cohomology.
U is fixed, I see.
U is fixed. Then
Okay,
we look at
yeah.
this, and here we collect our possible parameters.
So the uniqueness is lambda is unique.
Yes, lambda is unique.
I mean, lambda fixes 5. So lambda, okay.
Let's write lambda to make it very precise.
Okay.
Up to multiplication of lambda by a number.
You said it clearly, but
Right.
I was confused.
No, it's very good to say it here. This is the game we're going to play. We need to compute lambda. Let me give examples. First, I will give a very simple example. Second part. example 1 is a warm-up, a very simple example, of rank 1. We look at this differential equation. The solution is this algebraic function, 1 over the square root of 1 minus t. This must have to do with the zeros cohomology of a simple variety. So x is given by 1. We probably divide it by the group plus minus 1 to make it a 1 point. But still it's a family. The point changes with t and there is this differential equation. So our story tells us that this should be a p-adic analytic element. There is no choice here, up to multiplication, right? But the p-adic analytic elements, they also, you can multiply them by numbers.
What do you mean by equals to plus minus 1?
That you have x squared, so you can multiply by plus minus 1. There are 2 points, 2 solutions to this quadratic equation, but when you divide by plus minus 1, there will be 1 point.
But then there is no square root, maybe. I thought you were looking at the primitive part of
No, no.
0.
Yeah,
You just
x
choose.
squared and 1 minus t, so okay.
When you mod out by plus and minus 1, I think you lose the square root.
Yeah, it becomes x.
But you're looking at
Maybe
h0
let's
of
not
x.
divide.
Okay, so maybe 2 points.
Yeah, yeah. H0 of x of primitive will do what you want.
Okay, but let's just check that this is a p-adic analytic element to get the understanding why they appear in this picture. Simple understanding. When p is not equal to, this can be done by computation. So we just write it like that. Where q is the polynomial 1 minus t to the p minus 1 minus t to the p divided by p. And this is a polynomial with integer coefficients. And then this can be expanded in a formal power series. So what we get is these are p-integral numbers. They only have powers of 2 in denominator. So this series converges p-adically, and modulo any power of p, we can approximate by rational functions which have 1 minus t, powers of 1 minus t in denominator. So this belongs to the field of p-adic analytic elements. Right. And example 2 is our main result that I want to present. It will be for work pencils or work pendants, as in Alexander Corral's talk. So we look at x given by this equation, a hypersurface. In Alexander's talk, they were given by homogeneous polynomials, and that is a compactification of the historic hypersurface, but it's the same thing. It's easy to write down the transformation. So we look at the n minus first Gram cohomology of X, the middle cohomology. And then for hypersurfaces, their middle cohomology can be computed using differential forms on the complement. And therefore, there is this nice period function attached to this family. Let me call this polynomial here g of x. And, so my hypersurface is 1 minus t times g of x equals to 0. This is the equation of the hypersurface. This function, it can be computed, like if you expand this as a formal power series, it will be the sum of constant terms of powers. So this is the sum of hypergeometric function to which we substitute t to the n plus 1. And this is manipulated by the following differential operator. Theta to the n minus n plus 1 t to the power n plus 1. Theta plus 1. Theta plus n, where theta is the logarithmic derivative. T times t over t.
Can you raise the board?
This is a hypergeometric operator. In standard terms, the vectors alpha and beta are 1 over n, 2 over n, up to n minus 1 over n, and betas are 1, 1, 1, 1, but you substitute this for the variable n plus 1, t to the n plus 1, and this is a form to write the hypergeometric.
Is the first example not just a specialization of the second?
Oh.
Very clever.
Yes.
Yes.
Yes. Okay, so now we generalize.
Amazing comment.
Yes. Okay. We solve, to write the matrix of solutions, we solve this differential equation. It's convenient to solve it near 0. So let me call this power series f0 of t. It's a solution. But there will be non-power series solutions as well. So the first of them will be this power series. Then there will be a log solution, which is f0 of t times log t plus another power series. Second power series and so on. So there will be n solutions. This is sometimes called the standard basis. And then we consider
This is also Frobenius.
Frobenius, right?
Frobenius.
But I don't want to mess it. One Frobenius with the other one.
Like two Greeks. Yeah.
So u of t is the explicit matrix like this, where theta I, y, j, where I and j go between 0 and n minus 1. N by n fundamental matrix of solutions to this differential operator. some p-adic zeta values in it.
There is dry and wet solution.
So, theorem. The Frobenius structure. Oh, I didn't say that this phi of T, the family of Frobenius matrices, is called the Frobenius structure. It's in the title of my talk. The Frobenius structure for work tensors is phi of T given by this formula with lambda of the following form. We write 1 p square and so on the diagonal, 0 row. And now there will be n minus 1 p-adic numbers, which I'm going to specify. Now the second diagonal has lambda 1. The third diagonal has lambda 2.
Product of two nice matrices.
Where lambda j is the coefficient of xj in the power series expansion of this function. Where gamma p is the p-adic gamma function, the p-adic interpolation of n factorial, Morita's p-adic gamma function. Okay, I have to say this is an explicit Q-linear combination of p-adic zeta values, products of p-adic zeta values of total weight j. And this is seen from the formula. Just as the classical p-adic gamma function had this expansion at 1, which involves all zeta values, for the p-adic gamma function, it's more convenient to write this expansion at 0. But it also involves all p-adic zeta values. Okay. For example, here the expansion looks like that. So lambda 1 and lambda 2 are 0, and lambda 3 is a multiple of the p-adic zeta of 3. This case was actually computed more than 10 years ago by Ilya Shapiro. And this was more or less the only case when this matrix lambda in families was computed, because the methods of p-adic topology they seem to be complicated. So we invented some tools which make it easier, and we were able to compute it when there will be zeta values, all zeta values involved in this particular example. Yes?
This formula of a logarithm of p gamma function is log gamma p 1 plus x, no? Is it, are you sure?
No, it's at 0. This expression. This is the power series at 0.
1 plus x, no?
You can rewrite it at 1 plus x, of course, because there is a functional equation, but it won't be as nice as this one. So, this fact was conjectured by physicists also a few years ago, that parameters are Q-linear combinations of zeta products. This was conjectured for Calabi-Yau families of hypersurfaces. By Candelas, De La Osa, and Van Straten. Not quite physicists, but they made a conjecture and they published the numerical data around 2021. But we learned about this conjecture from Duke Van Straten back in 2017 in Australia. And this was the time when Frits and I separately started to think that this is an interesting question. I also want to say...
It's obvious, I guess, you said the coefficients have nothing to do with p, at this minus 8 over 25. So the formula is universal.
Yeah, right. So this is a big part of their conjecture, that expressions, these Q coefficients in the expression are independent of p, just like that. And moreover, they interpret them in terms of gamma conjecture.
A beautiful gamma conjecture.
Yes.
Because presumably you
So this must be the case of the gamma conjecture. For the mirror manifold, but I didn't want to go into mirror symmetry because we do simple things on one side of this mirror symmetry.
Would it be always lambda 1 and lambda 2 0 for...
Yes, this is obvious from this formula. This thing here is not nice, and it cancels in our expression. Secondly, this is a hypergeometric example, but we can do non-hypergeometric examples as well. And the fact that zeta values appear here is not related to the hypergeometric nature of this equation. In our paper, we have another family, this one. Right, theorem prime for this family. There is another nice expression, but Picard-Fuchs equations for this period function are non-hypergeometric. When n is growing, the number of singular points is growing. Here, lambda j is the coefficient of xj, so x to the j, in another expression, 1 over j factorial minus 1 to j minus interestingly, this is independent of n. So this gives numbers. I don't know why. Another nice formula of this kind.
It's independent
Of n. These are families in spaces of growing dimension. The differential operator depends on n heavily. To compute these differential operators, you need work.
Oh, this n.
Yes, but with lambda j, like when you increase the dimension, in u numbers that come, they only come after, like only one u number appears in this case. But it's special, it's a detail which is not important.
No, it's very different. So in the first case, the coefficient in a fixed power series. So in the first case, the work case, lambda j is the coefficient of the fixed power series. So you know the generating function lambda j. Can you write the generating function lambda j t to the j also here in closed form?
I don't understand.
Here, in this form at the top of the board, lambda j is the coefficient of x to j in something that doesn't contain j. It's a fixed power series.
No.
Here, on this board,
Here?
there's no j.
And here we have.
And here, so I'm asking,
I don't know.
of course, every lambda j is the coefficient of something, namely the generating function, some lambda j x to j. I'm asking, have you worked out the reason? It should be quite easy.
I mean, the generating function, but it's only the beginning. And then
I know, but actually that's another question that's for afterwards. I
Okay.
think
might be
you don't have to
interesting.
truncate it n.
Right.
There should be an n by infinity because it does the same thing.
So it might be a stupid question, but before you erase those
These
things,
things.
the coefficients of the t to the n plus 1 times k in f naught of t, the Hausdorff series of f naught of t, you have like n plus 1 times k factorial divided by k factorial to the n plus 1, right? But that's looks a bit like similar, maybe just a coincidence.
Like that expression, right? So what I wanted to say is that this must be a coincidence. That's why I'm showing the second example. It's not. This is not an easy computation.
Okay.
The computation doesn't use the differential equation and hypergeometric function. To compute these numbers, we need to construct the Frobenius structure, and the construction must come from geometry. The differential equation doesn't tell us what are the proper values of parameters. Well, I don't know a way to do it through through the properties of the Frobenius structure, 1, 2, and 3, which I wrote at the beginning. This sounds like a complicated approach, like analytic approach, how to detect lambdas from p-adic analysis. But we will do a geometric construction which constructs this matrix with the matrix phi of t with the required properties.
Is this kind of coincidence happens for your case, that theorem prime? Is that?
That
No,
depends on.
it doesn't look like that.
Oh.
In theorem prime, differential operators are complicated. We just can produce them numerically, one by one. We can program them, but we don't see any pattern.
Oh, you don't see any of that.
It will be a differential operator for the n-dimensional family, n dimensions, n-1 dimensional family. The differential operator will be again of order n, and we even do not know if they are irreducible. Here, for hypergeometric function, there is a simple criterion, and there our colleagues computed irreducibility with the computer up to n equals 30. And actually, in that theorem, I should have added that only when L is irreducible, this is the answer.
But
Up to n equals 30, that theorem is true.
But if it's mom, then it's irreducible. Because
It's small.
then it's irreducible. Yeah. You cannot get.
Let me show you this after. Okay?
So maybe a simple question while you're raising the board. The zeta p3s that you see here, I remember that numerically they would see the usual zeta 3s. Instead of Frobenius, they use monodromy. And but I seem to recall they could not prove that it should be zeta 3. They numerically observe it. Or has this been proved, or does your result indicate?
So, what do you mean about the usual zeta 3? Where do they see it?
So the analytic continuation from one singularity to the other one, there is a zeta 3 popping up.
You mean among a priori constants of this differential operator?
Yeah, I mean, at least in the case
I don't quite know. It doesn't seem like it's same series, that we can get this series from non-p-adic constructions. I don't know. Okay, so in the second part of my talk, in the last 20 minutes, I will explain how to construct Frobenius structure on Biram cohomology. So I will explain the p-adic operation on differential forms and also a result which gives a method of computation of such structures.
So you don't write the explicit expression of periods in the second exam. You don't need.
No. So, part 2, explicit computation. The p-adic operation on differential forms. What we do is only for cohomology of hypersurfaces. We developed some explicit methods in this case, and this goes back to Dwork. When Dwork proved that zeta functions of hypersurfaces are rational, this is the result I started this lecture with, he already noted, basically, now we can say that he noted that there is this explicit p-adic operation, but it took time to write it on cohomology, right, properly. So we will take a polynomial with coefficients in some ring of characteristic 0. I will denote it by R. It's convenient to work with Laurent polynomials, as you see in my examples before. R is a ring of characteristic 0. For example, can be Z or polynomials in one variable t to do families and single varieties. And the algebraic variety will be the hypersurface of zeros of this polynomial. And then the Biram cohomology of X can be computed by using differential forms on the complement. It's a trick in algebraic geometry. So, okay. Due to Griffiths and Battery, we can write it as follows. These are differential n forms on the complement, where H is another Laurent polynomial with coefficients in R, but modulo exact forms. And, well, probably this formula is for the primitive part of cohomology, to which our modules in this example is actually related. Let me introduce delta, the Newton polytope of F. This is the convex hull of exponent vectors which occur in F. It's a lattice polytope in Rn. R is the real vector space. For example, when F is like this, then delta will be here the exponent vector is 1, 0. Here it's 0, 1. And here it's -1, -1. This is delta. The polytope is independent of the coefficients. We only look at exponent vectors. We can vary coefficients and stay with the same polytope. So it turns out that the same computation can work if we look at less forms than all forms like that. So we can also assume that the support of H is in m delta. When we divide H by fx to the n, then H is supported in m delta. This also works. And this is the result with the So I will denote this by omega f. Here it's an R module divided by d omega f, which would be exact forms inside. On this module, there is a natural filtration by the order of pole, by this M. Where omega fk are forms with M between 1 and k. And this projects to the Hodge filtration on the Dirac quotient. And also one can give a weight filtration in terms of the Newton polytope. This is when we restrict, we have to introduce some rudiment topology on delta. For example, when we restrict here to H, which is whose support is in n times the interior of delta, this will give the lowest weight part. When we add the faces of codimension 1, this will be the second part, and so on. And actually, in the theorems, we work with this lowest weight part, which also will correspond to the cohomology of compactification. And then Battery tells us that if this delta has extra properties called reflexivity, then this will compactify to Calabi-Yau hypersurfaces. So that model makes sense to target the conjectures of physicists. Okay. So now the crucial thing is the possibility of expand these forms as formal Laurent series. The trick which we understood with Frits is that this formal expansion plays a role of integration over complex numbers. These are our cycles. And there are different ways to do formal expansion, which corresponds to different possibilities for topological cycles. Not to waste much time on this, I will give an example of a formal expansion, which is very simple in our situation. Formal expansion of differential forms. Just in this case, when f is 1 minus t times g. In this case, we can use this fact so it's a series for 1 over 1 minus t to the m. You write down the coefficients. I'm using them here, some combinatorial k plus m minus 1 choose m minus 1. So I'm substituting t times g. Anyway, what we get converges p-adically. So there will be a formal expansion of the form sum over vectors in z to the n. Assume we are in n dimensions, n variables x, depending on t times x to the v. This is the product, x1 times v1, x2 times v2, and so on.
So you're assuming that 0 is superposition in your interior? Yeah.
Actually, this will work.
No, I mean the form of the denominator.
Oh, yes, I do. Right. 0
in the interior.
But this is part of reflexive, what she always says.
I'm not assuming reflexivity, but yes, this is a part of the reflexive, but we do more general situation. So this is just one example of a formal expansion. There are other examples. In any situation, you can do expansion with respect to vertices of delta by just picking the monomial corresponding to the vertex and doing a thing like that. Of course, you can also do expansions in local coordinates, but then you have little chances to get rational expansions with rational numbers or nice rational functions. So to do number theory, we like expansions which are rational. Of course, there are examples when expansions in local coordinates are good, but this method somehow works in theorem cohomology quite generally. And now this p-adic operation on differential forms is given by a formula which one can see already in the work of Dwork. It's on formal expansions. Cartier operation, which sends the sum to the sum Cp times V x to the V. It looks like when we use different expansions, this will be a different operation, but not quite. They are connected. One can compare Cartier operations for different expansions. So basically, there is one guy like that. But when we start with an expansion of a rational function, we destroy it here. This is no good. This is not in theorem cohomology anymore. That's why it's essentially p-adic. It turns out that this can be approximated by rational functions with powers of something in the denominator, but that something is not f, one needs Frobenius lifts. So Frobenius lift is a homomorphism on the ring of coefficients such that sigma of R is congruent to R to the P modulo PR for any element of the ring R. And then this Cp maps omega f to the p-adic completion of omega f sigma. The p-adic completion. F sigma is when you apply sigma to the coefficients. For example, in our situation, F sigma will be 1 minus t to the p g of x, when sigma is just tracing the variable p to the power p. Then it's an easy lemma that this thing on this side can be approximated by rational functions, but with powers of F sigma in the denominator. And this lemma goes as my simple example in the beginning, more or less. It's really simple. Now, this Cp has very nice properties. It preserves exact forms. We have to pass to p-adic completion of exact forms, but that makes no difference because the theorem quotient has finite rank. So then, whatever we do, it doesn't change the theorem quotient too much. So it descends to the theorem quotient, and the matrix of Cp in the theorem quotient is our Frobenius structure. But what I said up to now is not enough to compute it. So to compute it, I want to present the second result. And this second theorem I want to show is maybe the main achievement of our project with Frits, which lasted for several years. It generalizes what Katz did in the 80s. And he called it internal reconstruction of unit root F crystals. So if R is periodically complete, and we have this assumption R can be a ZP but not QP. And the case Hasselbalch condition is satisfied. Then omega f splits into the direct sum of this part. Well, k in this theorem can be any integer bigger or equal 1, plus something I'm going to describe in this theorem, the other part. This is the part of the Hodge filtration, and this is a free module of finite rank, in which you can easily write the basis.
Can you maybe say again what omega for k is? Because what you wrote is just this set of integers.
So we look at differential.
No, but what is written, I think, is not what you meant, or is it? It's just the integer is 1 of the k.
No, these are forms like h over f to the m, dx over x.
So it's the piece of Hodge filtration.
Let me write.
No, but it's interesting, but what is written is always not what you mean.
Yes, these are differential forms.
So it's the piece.
These are like h of x over f of x to the m, the product dxi over xi with m less or equal to
Okay, thank you.
the order of pull along the hypersurface. That's a filtration on our model, differential forms. And this is sensitive. And here we describe the filtration. And the whole trick is in what it is. It is described in explicit arithmetic terms, where fk is given by differential forms with the special property of uniformal expansion. That for every exponent vector, the GCD of v1 vn to the power of k divides the coefficient cv. You can also write it in terms of the Cartier operator. These are forms such that for any s, when you apply the Cartier operator s times, this is divisible by p to the sk, and that omega f sigma applied k times. This is sometimes called the slope filtration in the theory of crystals, but this characterization is important for computations. What we do, we use expansion coefficients. We write something like that. Choose a basis in omega fk. Right? That Cp omega I is the sum phi ij omega j modulo fk. Now take coefficient at x to the p to the s v. So some vector v. That gives the linear equation here, modulo p to the power ks. There will be a linear algebra of congruences. But since S can be arbitrary, these congruences will converge. We are getting p-adic approximations to the matrix entries of the Cartier operation. In practice, we have to go down in this split infiltration so that Fk is inside exact forms. Then we can do this linear algebra. And then we also have to describe exact forms inside. And this is again linear algebra, and this produces the Frobenius matrices. Okay, that is all I wanted to say.
Thank you for your talk.
So are there? Yes, please.
This seems to be the p-adic counterpart of the complex conjugation, no? Because in the complex context, if you take a complex conjugate, another piece of the Hodge filtration, then you have a kind of direct. So, and actually another question. So, what's the difficulty to do the things for usual hypersurfaces in projective spaces, not the one given by Laurent? I mean, the physicists used Laurent because you can calculate periods and so on explicitly. And
well, that's a particular case in this projective.
no, I
Other F tells us that
given by
hypersurface under some conditions, like delta regularity of F, our hypersurface will converge, right? But not in the usual projective space, in a bit more complicated projective space, which is related to delta.
So the final thing that you didn't have much time to explain, is that already appeared published in the archive? Or?
Yes, this is a theorem from 2021, but it was published in 2023. It's called Dwarf crystals 3. We have 3 papers called Dwarf crystals, and in the first 2, we do the case K equals 1 of this theorem, which was basically done by Katz in 1985. It's called when K is 1, F1 includes exact forms. So the quotient by F1 will be smaller than the rank cohomology. And this is called the unit root part in p-adic cohomology. And Katz did it on expansions of differential forms in local coordinates. But he has some geometric assumptions like smoothness of hypersurfaces. And we wanted to do it sort of simply and combinatorially to have applications in number theory. These results apply to prove some classical congruences in number theory.
Other questions? So, thank you.